through case studies. I plan to evaluate the improvements and clinical implications I found, and I also plan to delve into the challenges that I've came across, along with the future developments of the field, along with the conclusion. Okay, so to start my introduction, what is CT? So computed tomography is pretty much is an imaging technique that consists of a beam of X-rays being aimed directly at a patient and being rotated around the patient's body. Pretty much produces signals that is processed and pretty much generates cross-sectional images, which we call slices. And these 3D images are formed of the patient through multiple successive slices. And then CT technology pretty much provides a comprehensive view of the body's internal structures, which enables accurate diagnosis and effective treatment planning. And continuing on with the introduction, I'll briefly go over photon counting CT. So photon counting CT is an innovative CT technology that utilizes a direct conversion X-ray detector, and PCD directly records incident X-ray photon energies as electronic signals, which provides more precise data, which we call direct energy recording. And then the technology utilizes semiconductor materials to generate these electronic signals from the incident X-ray photons, which enhances image quality and diagnostic accuracy. And then the schematic on the right basically shows the process of PCD, in which it uses a semiconductor to directly generate positive and negative charges, with negative charges going to pixelated anodes to record each individual photon and its energy. And for the last part of the introduction, I'll be covering conventional energy integrating detector CT. So for conventional energy integrating detector CT, it's pretty much the conversion of X-ray photon energy to electrical signals through a multi-step process. The first step would involve scintillators, which are materials that emit light when exposed to X-ray photons, which is utilized to generate visible light when interacting with the photons. And then the generated light is then converted into electrical signals using photodiodes. And then on the schematic on the right, uses a scintillator to generate the visible light when the incident X-ray photon hits them. Then the light is recorded by a photodiode with reflectors in between detector elements to reduce crosstalk. And then for the first case study of today, I'll be going over focuses on the lumbar spine. And pretty much this study compares photon counting CT and conventional energy integrating detector CT using images reconstructed with a bone kernel. So pretty much first we analyze axial images from a 27-year-old patient using PCD as shown through images A through C, and compared them with those from a matched 25-year-old patient using EID. And this allowed us to directly compare the imaging capabilities of both technologies under similar conditions. And one of the key findings was the difference in radiation doses between the two modalities. The CTD volume, which measures the radiation dose, was significantly lower for PCD at 4.5 milligray compared to 10 milligrays for EID. This highlights a major advantage of PCD in reducing patient exposure to radiation. Both examinations also use tin perfiltration to enhance the image quality, which also ensures that the comparison was fair and focus on the capabilities of the detectors themselves. And then there's also a subjective assessment by 3 independent readers, which revealed that the overall image quality was excellent for both the PCD and EID scans in these assessments. So this demonstrates that PCD can achieve similar or even better image quality at a lower radiation dose, which is a significant benefit for patient safety and diagnostic accuracy. And here's just a summary of the lumbar spine results in terms of radiation dose. So briefly, CTD volume, which stands for computed tomography dose index volume, had a value of 4.4 plus or minus 1, which shows it's a substantial reduction in radiation exposure, making PCD a safer option for patients. And for SSDE, which is the mean size specific dose estimate, they received a value of 6.2 plus or minus 1 for the study. And that value showed a minimization of patient-specific patient radiation dose in comparison to EID, which received a value of 14.2 plus or minus 1.8. and that value was more than double of PCD. And altogether, this ensures safer imaging practices and reduces the risk of radiation-induced complications. And then just briefly going to the side of EID, the CTD volume was 11.1 plus or minus 1.9. So that obviously showed a higher level of radiation exposure, which increases the risk of radiation-related health issues for patients. And then EID tried to also implement a tube current modulation, which was about 398 plus or minus 71. That was supposed to manage the radiation exposure. However, even with that implemented in, EID still had a higher overall radiation dose than PCD, which did not have a tube current modulation. So that also implies that EID's dose reduction strategies are less effective for radiation safety. And then moving on to the results for the image quality. So for PCD, we would first start off with CNR, which is the contrast to noise ratio. The value was about 33.6 plus or minus 3.3. And when you compare it to EID's 29.3 plus or minus 4.1, CNR shows that the higher CNR allows for improved tissue differentiation, which is critical for an accurate diagnosis for a patient. And then I'm pretty much going to dive really briefly into like the reading scores of readers. So image quality based upon the images. For PCD, they received a median score of 4. That the range for readers typically was the lowest was 3, but the range was typically 4. This provides more detailed and clear images, which improves the visualization of anatomical structures within the lumbar spine. And then the inter-reader agreement was in the range of substantial to almost perfect. So the value was about 6.686 to 0.81. This range ensures consistent and reliable image quality while minimizing variability. And then for EID, some of the parameters were comparable image noise and signal to noise ratio. These parameters show that EID doesn't surpass PCD in terms of providing clear images, since the values were much, much higher. And then the voxel volume was 0.18 plus or minus 0.04, which is very similar to PCDs. So that ensures that EID doesn't provide any significant advantages over PCD thus far. And then for the image quality, 2 readers gave a median score of 3 and 1 gave a median score of 4. So this also shows variability, suggests that EID image quality may be inconsistent since some voters rated 3, but some rated 4. So this would also lead to less reliable imaging results. And then I want to move on to case study 2, which would happen to be on temporal bone imaging. And this would focus on the modulation transfer function. So to begin, the modulation transfer function pretty much measures the ability of a CT system to resolve fine details. And for our MTF values, pretty much that would indicate spatial resolution performance at different frequencies. So for comparing both technologies in this case, the higher performance PCD shows better modulation transfer function resolution performance compared to EID. And pretty much how you can see that is on the curve on the left. Pretty much PCD is curved up higher in terms of the values. The curve is always pretty much higher majority of the time on the graph. And since the curve is consistently higher, this would indicate a superior resolution. And also as we proceed further on the x-axis, which is the spatial frequency axis, PCD would also capture finer details more effectively as well. And then pretty much on the bottom is a table of the spatial frequencies that was heavily focused on in the study, which was at 50%, 10%, and 2%. And it pretty much recorded the values of the spatial frequency for each technology as well. And continuing with the case study, and here are some of the key findings in regards to the spatial resolution for the temporal bone imaging. So PCD demonstrated superior in-plane resolution, as shown by the curve that we demonstrated in the last slide, which was represented by the higher spatial frequencies at 2%, 10%, and 50%. And it also was able to demonstrate better depiction of anatomical microstructures, which indicates the ability to resolve fine details with greater clarity. Images were consistently preferred for all assessed structures, reflecting higher spatial resolution and improved visualization of sub-millimeter features. And in comparison to EID, pretty much as shown by the curve, we receive slightly lower spatial frequencies at those values, which indicate lower in-plane resolution. Images showed reduced delineation of fine anatomical structures, and pretty much they are also less favored compared to PCD, and the reason why was due to thicker imaging slices, and there was a preference for thinner images throughout the study due to the values being fluctuating depending on thinner or thicker slices of images. And this highlights the advantage of PCD in being able to achieve higher spatial resolution and better visualization. And the next part of the case study will dive into the impact of image thickness on these on noise perception, at preference, and temporal bone imaging. So for the preference for thinner images, PCD 0.25 images, as shown on the left, despite potentially higher noise levels at times, were preferred over thicker PCD 0.6 images. And this would underscore the significance of image thickness and noise perception and preference. And throughout this study, as well, the least preferred EID protocol, based upon the graph, was typically out of the results, EID 0.6 images were found to be least preferred among the three protocols, and this suggests higher noise levels in a majority of cases compared to the other two. However, there are times where it's not always not going to be the same one being higher than the other. It just sometimes fluctuates, but there's always the common ones being either highest or lowest. And then going back with the readers, there's always a consistent preference. So despite potential variations in the noise levels, readers consistently favored the thinner images as mentioned before, and this indicates a discernible trade-off between the noise and image thickness. And then this would be a slide just summarizing the key facts on image noise and what we learned. Pretty much, we were able to consistently display significantly lower image noise levels, and then pretty much the thinner image slices in PCD facilitated superior noise reduction, which would minimize the noise artifacts. And then we were able to utilize direct energy conversion, which effectively mitigates the noise across various image thicknesses that we would be encountering. And in the regards for EID, we basically exhibit consistent higher image noise levels, and it's particularly evident in thicker image slices. And with the thicker image slices in EID, this contributed to elevated noise levels, which obviously, in fact, would impact our overall image quality. And then pretty much the expected improvements and clinical implications of photon counting CT thus far have been image quality, where we expect high resolution images even at low dose levels. We expect the significant reduction in radiation dose up to about 85% thus far, making CT scans safer and more viable for routine screening applications such as lung cancer. We expect there to be a reduced dosage of contrast agents while maintaining identical image contrast, which is crucial for patients with impaired renal function. And so far, the technology is able to offer multi-energy data with each scan, improving diagnostic accuracy by clearly separating contrast agents from calcifications, enhancing treatment decisions, and also we expect there to be reduction of artifacts such as beam hardening, metal artifacts, and blooming, which would in result would give us clearer images. And then briefly, some of the current challenges of photon counting CT thus far, we expect there to be a crosstalk. So pretty much with that being said, crosstalk would be when photons pretty much interact with silicon detectors. Typically, a process would undergo Compton scattering, which is when you deposit some of the energy in one detector element in the other. And while Compton scattering is less common in cadmium telluride and cadmium zinc telluride detectors, the positive energy can potentially release fluorescent X-rays, and these X-rays may be absorbed by neighboring elements, which can potentially lead to inaccurate measurements. And this is just a crosstalk visual of what I found as well throughout the study. So pretty much for diagram A, this is an example of fluorescent crosstalk, which is basically when the X-ray photon would deposit a portion of its energy in an incident detector element, while the rest of the energy would then move over to the fluorescent photon. And due to this would then generate charges at another location, which is which would be another detector element. And then diagram B would just be an example of charge sharing crosstalk. So that's pretty much when the X-ray photon is absorbed at the border between two detector elements. And due to that, the generated charges are divided and then registered in both elements. And both play a role in impact on image quality in how the fluorescent crosstalk and charge sharing pretty much they are basically pretty much being recorded in around detector elements. And due to that, we basically expect there to be a big degradation in the image quality we expect.
So Michael, you're at almost 16 minutes now. So can you proceed to the conclusions and finish up?
Oh yeah, sorry about that. And I'll just quickly just like hit on this point real quick. Another challenge that we would expect is power up as well, which is pretty much when photons arrive at a detector too fast, which results in electrical pulses overlapping. And that's another challenge that I identified throughout the study. And this is just another visual as well of the power-up visual of the delayed photon arrival and simultaneous arrival. And for future developments, I identified that coincident counting and contrast material development were ones that were coming up constantly in terms of being able to improve PCD CT. And just the conclusion, I was able to identify enhanced performance in this technology. I was able to identify that the radiation dose reduction is consistently being used and finding ways to improve lower radiation dose. And also I was able to identify improved diagnostic accuracy throughout my studies and also identify challenges and limitations. And also with the future developments, looking ahead in coincident counting and contrast material development, they're both also expected to further enhance PCD's capabilities as well. And then this is also my references that I use for my studies. And thank you.
Great. All right. Thanks very much for that review of photon counting. And what's interesting is the MTF data that you showed seemed to be in the two-dimensional plane, right? And then the slice was dealt with as kind of a separate dimension as opposed to looking at the MTF in that direction as well, which I think if you were to redo that study, you would probably do that, right? You would image things in the, say, the coronal plane and measure the MTF in the, say, XZ direction as well. And that would show a much better MTF for the PCCT.
Okay.
Okay, cool. Thanks. Let's keep going since we need to keep to about 15 minutes each if possible to get everybody in. And let me see who wants to go next. Ari, do you want to go next?
Sure. Can you hear me?
Yes, I can hear you loud and clear.
Okay.
And take the screen.
How do I do this? Can share screen.
Just share screen. Yeah, we can see it.
Okay. Hello, my name is Ari, and today I'll be talking about scar imaging in echocardiography, and specifically on quantifying cardiovascular calcification. So here's an agenda. So I plan to really quickly go over the background on cardiovascular classification again, and then go over the basics of ultrasound, physics of ultrasound, and the post-cancellation technique, and then go into E-scar method, which is the focus of my study, or what I'm trying to simulate for this project. And then towards the end, I will show some of the MATLAB simulations I did and a lot of challenges I faced. So just the conclusion is that I wasn't able to successfully simulate it, but I will talk about why what challenges I found and what I think could fix in the future. So quickly first, the cardiovascular calcification, just a recap. So it is the deposit of calcium in the cardiovascular system, and particularly around areas where high mechanical stress happens. So like heart valve happens a lot, or anywhere with turbulent flows. This process usually begins, usually before this happens, usually there is fibrosis and then stiffening of the tissues, due to stiffening of the tissue due to fibrosis or other sort of chronic inflammation. And then once you reach the stage of calcification, it could lead to other more serious complications such as stenosis, or your valve would just stop moving if it's on the valve. It doesn't move, it doesn't close anymore. And I won't go into detail of this, but if I have time, I can go more into detail of anyways. So anyways, detecting these changes early is crucial for effective management of the symptoms. And because usually there are no symptoms, people don't realize it until they get like MRI or other sort of imaging for other things, and then they incidentally discover it, or they don't realize it until it gets too bad. So if there's a reliable way to use ultrasound, which is something that is relatively inexpensive compared to other imaging technique, it's portable, it's non-invasive, and there are no radiation exposure comparing to MRI and CT scans. It will be great for regular checkups. Also, it's commonly found in many clinics because it's less expensive. But the problem with that is that there are no existing method or standardized method for quantitatively analyzing these data. So a lot of time you or the patients will have to rely on how experienced the technician is, or subjective diagnosis. And so, oh, I went a bit too quick. So anyways, to address this, there was a paper, I think it's in Italy, Garpazzi et al. Developed the eSCAR technique, or the eSCAR method, that uses pulse cancellation to enhance the contrast in the ultrasound images. And by selectively enhancing the signal from calcified and scarred images, the fibrous tissues, they can then use it to quantify quantitatively improve the precision of their diagnosis. So in order to, before I talk about the eSCAR method, I'm going to go over really quickly the basic knowledge of ultrasound physics. So ultrasound physics, sound is a mechanical sort of wave, which is different than electromagnetic waves in the way that it relies on compressing and depressing a medium, and therefore the speed is determined by the medium. Specifically, it depends by two factors: the bulk modulus, which is how elastic the medium is, and density of the medium, how densely packed the medium is. Another two things that two parameters, the two determining characteristic sound would be frequency and wavelength, which in turn determines the resolution of ultrasound, as well as how far the sound waves can travel before it attenuates into nothingness. Well, it dissipates into heats and or turns into other things that you can't read, or the ultrasound is not useful for the ultrasound. And so here is a quick chart of it's blocked by the, I hope you can see it on my end.
Yeah.
It's blocked by the
Yeah, we can see the chart.
okay. Cool. So it's a chart of relating the density of different materials, or we often encounter in ultrasound, to the speed. And you can see that air, being less densely packed, travels more slower, whereas something like a bone, ultrasound travel faster. Although I believe that the bulk modulus or the elasticity has more effect than density have on the speed of air. Okay, another parameter of the ultrasound that is very useful is the acoustic impedances, which is associated, again, is intrinsic property of the material. And I mention this because ultrasound, basically they, where did my note go? So ultrasound relies on listening the echo. You emit a pulse, and then you wait a little bit for the echoes to come back. And when the sound wave travels between two mediums, depends on the impedance differences which you can see in the refraction coefficient R. Part of it is going to go through and a part of it is going to reflect back. And that depends on the impedance difference. So if you have something that goes from a very high impedance into a very low impedance, for example, let's say the air in the lung, most of it's going to reflect back. And so you don't get, most of the sound wave doesn't travel through. And so that usually is an issue when you're going to do ultrasound of chest cavities because you can't really see into the lungs because it reflects back. But ultrasound relies on this sort of the information of the echoing back sound wave in order to determine and analyze the position and analyze the thing that's getting imaged. In this case, we're looking at heart. And here on the right, here is a quick chart of different acoustic impedances of commonly encountered human tissues. Okay, what is this plan? Oh, right. And so, as I said earlier, that ultrasound, you don't continuously emit pulses. You emit one pulse, you wait for the echo to listen to it, and then the longer you wait, the more information you get. But then the more, I think previously I mentioned that, right, higher frequency results in a better resolution, but then it loses, it attenuates away really quickly, whereas lower frequency, they travel farther, but the resolution is not as good. And on the right is a schematic of how ultrasound transmits, travels through the tissue, different layers of tissue. And so every time when it hits a difference between two different type of tissues, some of it's going to reflect back and then some of it's going to go through. And then there's also the attenuation issue as it slowly dies out.
So, Ari, I just want to give you a heads up. You're about halfway through your time. It's 7.5 minutes. So,
Okay, I will skip the part. Okay, so basic ultrasound, and there's a pulse cancellation. So what happened is that the pulse cancellation or pulse inversion technique, you emit, instead of just emitting one sound and then carrying back, you emit two pulses, and one of it is the invert other one. So when the first pulse hits something and reflect back, a part of it's going to cancel out the second pulses. And so it's relying on, but then that only happens when the medium you're hitting is linear, so uniform, relatively uniform. So if there's any nonlinear behavior, then it won't perfectly cancel out, instead will enhance the harmonics. As you can see on the right part, this image is kind of blurry, but the next one will be better. When the bubble, in this case, they use an injection, it consists of lipid-coated microbubbles, and which exhibit nonlinear behavior. So when the ultrasound wave hits it, and it doesn't reflect back in a way that will perfectly cancel out, and instead enhance the harmonics. And then you can tune your ultrasound to only listen to the harmonics. And then in that case, then you can selectively say, oh, I want to look at this part specifically. Usually they do this to look at blood flow or vascular structure. And here's a better photo of how that works out, where it enhances the harmonic signals. And so here is a example of a scan for liver cancers. On the left, it's just, a regular ultrasound. On the right, they use pulse inversion to enhance where the blood flow is. And so now I want to talk about E-scar method, which is for the heart. They use the same thing, but they don't do the contrast. Instead, they rely on the calcification or fibrous tissues introducing the nonlinear behavior into the tissue. And so you can see on the left, there's a standard ultrasound image. And on the right, most of it is canceled out because they're uniform and healthy tissue, but the scarring tissue that's being pointed out by the error is highlighted in the study. So highlighted in the images. And they can do this without injecting any contrast, which is cool. One less thing to have to deal with. And so here is another image also comparing the image on the very right is one with injected contrast. Image in the middle is without injecting and just using the E-scar method, which is some sort of sequence they use. And then image on the left is actually a cardiac MRI. And you can see that even though it's not as clear as MRI, you can still pretty accurately or relatively accurate comparing to the contrast image, enhance the part where there is a scar tissue. And so now I'm going to talk about my simulation attempts. So I originally want to use Python, but I found this toolbox with MATLAB, which does acoustic wave simulation that also takes account. You can play around with nonlinearity and also heterogeneity, and also it does both one-dimensional, two-dimensional, and three-dimensional simulations. So on the right is some of the parameters set up for this is two-dimensional heterogeneous medium that I did. This is on the top left, you can see that I did a 2-point pressure source, and I did a circular sensor mask around that pressure source, and then I varied the sound speed on the top and bottom. I did a different, I think the bottom I did 1500, and top I did 1800, and then the density, I also did a different, like, oh, this part of the medium is going to act differently in terms of density. Oh, okay. And so, and here's the result of a point sound wave propagating through, why is it so quickly? Well, it's much faster. Anyways, it propagates through the a homogeneous medium, and then the resulted sensor data on the right. Can I go to the next slide? Yes, and then versus a heterogeneous medium and the result of sensor data on the right. You can see that with heterogeneous medium, the echoing is a lot different comparing, can I go back to the homogeneous one? But these are just experiment trials to see if this program works. What I really wanted to do was to model some sort of model something after a biological tissue. So I tried to build my own quote unquote ultrasound transducer by setting the sensors and wave sources to be on the same locations like ultrasounds would be, and then created a sort of burst pulse source with Gaussian filter over it to mimic ultrasound pulses. And then I divided up, this is two-dimensional. I divided up the grid so that different part of it will have different medium density and velocity based on the previously provided table, where pericardium, which is mostly connected tissue, should have this density, and then myocardium is muscle, it should have this density, and sound should travel this fast, etc., etc. And I didn't get much success with it. It can detect that the change in tissues is perpendicular to the sound traveling through it, but other than that, it's not as clear as the one I did before when it's just a simple point source. And so as I was trying to figure out why, I found that they had a special input object in the toolbox called K-wave transducer that can be substituted for the source and sensor input. So I used it, but the problem is that it can be only, but previously I was doing two-dimensional, but so this object that the toolbox provide can only be used in three-dimensional simulation. So which means that it's very memory and CPU intensive and requires a GPU, which I don't have, for faster simulation. And on the right, it shows a graph of the input signal and the frequency spectrum generated by that I can generate with this object, the K-wave transducer. And so I tried to run something with it, but again, I cannot run a full simulation because it takes 2 hours even after I made the grid a quarter of the original grid size and get rid of everything else and just have a calcified circle in the pool of blood, I still couldn't reconstruct it, and that took 2 hours. And anything more complicated than that would take 4 hours, or even more, because it just never finished running. and would and so I couldn't simulate the post cancellation scar enhancing method that I wanted to try to see. So for future aspect, there are possible things I can try. I would love to, if I have time. Well, otherwise it would have been perfect because it's 3-dimensional. I could make my own 3D heart model to try to experiment or go along with the transducer that come with the toolbox. I can take slices or 2-dimensional slices of the model and run more trials. But I'll probably have to find a computer with a GPU to realistically run this experiment. So that concludes, and here are my reference. That concludes my presentation.
Okay, thanks. Sorry, it didn't work out that toolbox was efficient. That's like one of the risks of using someone else's toolbox, right? You get all of the bells and whistles they've programmed in, but you don't know basically how well it's going to run. But I think the initial simulation you did with the, array of receivers around the point source, that's pretty cool too. Okay, well, let's keep moving on. And
thank you.
You can give the screen back. Reminder, we're trying to stick to like 15 minutes if we can for these, if we want to get through them. Who wants to go next? Where's our participant? So Omar, do you want to go next?
Yeah, sure. I'd love to. Okay. Ari, could you just unshare your screen?
Yeah, I think you have to go to the top and say quit sharing.
Uh-oh.
Is she still there?
Oh, I'm still here. I will
okay.
just leave and I'll come back.
Oh, you can just unshare.
Oh, there. Oh, it worked.
Yeah. Okay, great.
Okay. All right. I'm assuming my screen is visible.
Yes, it is.
Okay, perfect. All right. Hello, everyone. In a case of deja vu, I will also be doing photon counting versus energy integrated detectors, comparative analysis of both X-ray techniques. So my name is Omar. So I'm going to be starting with my talk with a basic outline of what I'll be covering. So first, I'll be going into some very basic PCD EID basics, but we've already kind of learned a lot with Michael's very good presentation earlier. So I'll be a bit brief on that, but I will touch on a bit more in terms of the material science behind both types of X-ray techniques, as well as how the signals of each technique is conditioned electronically, and the key differences in image acquisition quality, as well as some simulations I made in order to display the effects of noise and how PCD kind of wins out in the race with EID in terms of CNR and SNR. So very briefly, we know that photon counting detectors, they quite literally count every single photon that hits the detector, and they convert all that energy, every single one, all the tens of thousands that hit the detector at any given time, into electrical signal. And because of this, it's theoretically possible that thousands can be processed at the same time, as well as having much smaller detectors, as you only really need something that can take in a photon, ideally bigger, but it is possible. And then, of course, with an energy integrating detector, instead of using a direct solid state material, it uses a scintillator, which produces light at the incident of X-rays, and then that light is converted into electrical signal via photodiodes, and it integrates the energy of several photons at a given time, hence the term energy integrating, and theoretically would not process signals as fast and would have to have bigger detectors due to the extra step in processing X-ray photons incident on material. So very quickly on the material science, PCD typically uses semiconductor material, the most popular being cadmium telluride, or sometimes if you dope it with zinc, the cadmium zinc telluride. And the reason this material is used is due to its very high atomic number, as opposed to common semiconductor materials such as silicon or gallium arsenide, which have smaller atomic numbers. So the bigger the atomic number, the smaller your Compton scattering. And the anode across I'm sorry, so there's a voltage across the solid state material with a very high voltage. And so every time a photon hits the solid state material, an electron hole pair is made, which then is turned into current due to the high voltage across the material, which then goes into detectors as electronic signal. For integrating detectors, energy integrating detectors, there's a scintillator as opposed to a semiconductor. And a scintillator is a object when it is hit with a certain form of energy, in this case, an X-ray photon. It produces a small bit of light, and that light is then detected by photodiodes. Now, this light, of course, is radial, so it uses collimators in order to prevent photodiodes close to each other from detecting the other photodiode's intended light pulse. So that is kind of like the crosstalk that was talked about in the previous PCD EID talk that needs to be prevented, especially in EID. I made a very simple little like graph showing the actual process of X-ray photon to signal for each modality. So on the left, we have energy integrating. So the X-ray photon hits a scintillator creates a light, photodiode detects it, sends it to a processing signal, as opposed to PCD on the right, where an X-ray photon just hits solid state material, the cadmium telluride, that immediately makes some electrical signal. So there's there's one less step in PCD detectors compared to EID detectors. For the signal acquisition, this will be for the PCD after the current is induced in the detector. It is sent through an amplifier that changes the current signal, right? Because it's a whole electron pair that makes current flowing electrons into a voltage signal, which then gets shaped by a waveform shaper. And then that eventually goes off to comparator circuits. And the comparator circuits look to see what energy level each photon is at, because the process of photon counting also uses energy bins. So it places different photon energies under different sections in order to reduce a very low level energy bin, which is typically noise. It's roughly around the mark of 20 keV, and then places the other photons in different energy bins, which is then for processing due to different attenuations through human tissue or what other tissue is being analyzed. All photons, regardless of their energy magnitude, are counted using this method. Even the low ones that will then later be discarded, as I will show in my simulations. For the integrating circuit, it's much easier because you use an analog signal known as an integrator. So that will then, of course, integrate over the energy over time, and that will take into account multiple photons, multiple energy beams, and create a what is known as a cumulative energy curve. And this data is then sent off to an ADC, an analog to digital converter, in order to then be processed by a computer or whatever program is used by the investigator. Of course, due to this, much lower magnitude photons carry much less weight in the broader integrated cumulative signal as opposed to high energy photons, which could lead to worse CNR and worse signal to noise ratio, as I will show in a bit. This is just a very simple diagram from the literature that kind of shows how this works. In the energy time diagram for the left, the energy integrating, we see this big curve over these two small ones, which represents the energies of the light being detected by the photodiodes into this broader cumulative energy curve. And then on the right, we have the photon counting detector, where both photons are counted and they are both separate, discrete pulses in the energy graph. Some very quick and easy quality comparisons I've seen in the literature between EID and PCD. As I do not have a EID or PCD X-ray in my apartment building, I'll have to use what is used by scientists and biomedical engineers. So in this image from Nakamura et al., we see a fish that is being scanned. On the left, on A and C, A zoomed out, C zoomed in, a photon counting detector was utilized, while B zoomed out, D zoomed in, an energy integrating detector was used. You can see just looking at the spines of the ribs of this fish, we can immediately see that there's better differentiation in C from the flesh in the background and the bones in the middle, as opposed to EID, where they're kind of blurring into each other. It's artifacts are more noticeable. It's much blurrier, which makes sense if the PCD does have, higher energy dosage. I'm sorry, not higher energy dosage, lower, smaller detector arrays, and is able to process every single photon and is able to differentiate between tissue much better than EID. Here's another one. This is an axial picture of an individual's coronary system. On the left is EID, on the right is PCD. Right, you can see this little chunk of calcium. It's much easier to differentiate. I mean, yeah, the left one's brighter, but it's blurrier, and it's much harder to differentiate the actual material from the background. This is very useful for diagnosticians and clinicians to be able to differentiate different tissues in a diagnostic process. So for the simulation, I made a very rudimentary MATLAB simulation wherein there is an array of detectors across a time scale. So you'll see a 129 by 129 mesh grid, and you can consider that as being like 129 detectors on the y-axis and 129 nanoseconds on the y-axis to kind of show how a detector is acting over time. And I'm going to simulate both pulses of a PCD as well as the cumulative energy curve of an EID X-ray. So PCD will have those impulses, while for the EID, because the energy integrated curve kind of looks like a Gaussian, I went with a Gaussian curve. So I convolved a Gaussian with an impulse to make a 2D Gaussian function to kind of simulate what that curve looks like, and then taking a cross section of the mesh grid. This is mostly an educational simulation to show like how noise is better treated in better dealt with in photon counting detectors. So this is just a noiseless incident of my photon counting detector. We can see on the left this mesh grid with 4 pulses across one detector at 65. So at the y-axis of 65 of different magnitudes. And then on the right, we can see that cross section where I placed some arbitrary constants, which are my energy bins, and I made them at 60K intervals. So obviously this is a clean image. This is an ideal scenario. This would never exist in reality. So, but it's to show you how it differentiates from a noisy one. So after adding some randomized noise, we can see that on the right, while there is noise, you can still very much differentiate each and every pulse, every incident of an X-ray photon over a time scale. This would typically be in nanoseconds, maybe even smaller. And usually if you're like, okay, my EO is noise, everything under EO is just discarded for energy acquisition, so that when it is processed through some program, you get a cleaner image with, high contrast to noise and high signal to noise ratio, as opposed to an energy integrating detector. So this is my ideal image of what a cumulative energy curve would look like over time. So if we can think of this as like multiple photons and their overall energy being integrated, this would be a perfect image. And obviously it's very clear what is signal and what is not. But once you add noise, it gets a little difficult to differentiate these lower photon energies down on roughly around the 60-50 time scale and the 80-85 time scale. It's much harder to differentiate what is noise to what is signal. And so as opposed to PCD, where you just look at the impulses and you can very clearly see the impulses, and the processing hardware will be able to, route those impulses to different counting bins, as opposed to EID, where it just integrates the whole thing, and you have to figure out how to get rid of the noise after the fact.
So can I ask a quick question while we're still on that slide? Can you go back to that?
Yeah,
slide?
sure.
So that I understand what's going on, the noisy EID capture on the left here, the axes, because your time goes to 120 as well, I'm getting confused what's time and what's space. Is this a 2D spatial detector on the left, which is just pixel number?
It's mostly so initially I was doing like a 2D spatial, but then it made more sense when looking at the energy diagrams online for it to be like the x-axis is time. So
Okay,
different like
even
yeah.
on the left, the x-axis is time.
Yeah, so even on the left, it's like different time slices. So 129 like time slices, and then on the y-axis is different detectors. So they're detecting over time. So detector one
Yeah,
up here has 129 time slices. So what it's detecting over time.
thanks.
Yeah, it's a little I should have labeled my axes for the mesh grid images, but um that's what I then tried to convert into the cross section here on the right. So that's how, just a very rudimentary way of just showing how we can actually like, it's a rudimentary way of showing how photon counting detectors are much better at discriminating against noise and are able to have much better resolution, spatial resolution, especially if you can have smaller detectors, lower radiation dosage since you don't have to worry about scattering at the detector. Of course, these simulations display how this noise is dealt with. PCD can allow for smaller detector sizes, greater contrast between tissues. And while the photon detector does seem to be the future of CT, most definitely, there are still some problems, as talked to in Michael's slides, especially in terms of pileup, where if you have two photons that are like right next to each other on the detector array, they can have some aliasing happen where it's very difficult to actually count those photons. It's very difficult to see what is one photon energy versus what is another. And of course, this can lead to oversaturation of detector cells, which is what kind of stunted PCD research for a while. These are my references that I've used. Special thanks to Nakamura et al. I found their National Institute of Health article on PCD versus EID CT to be very, very comprehensive, and I use some of their figures in my images. But yes, thank you. If you have any questions, please feel free to ask.
All right, thanks. That's cool. Can we go back to the slice where you have the one before this, I think, and the one before this, that one. Yeah.
Yes.
So now we're rocking along in time on the x-axis. We have one detector element, which is like the middle one, 64, which is giving photons of different energies.
That's right.
Okay, the noise baseline there that you've got is from electronics in the whole system, and you've eliminated that noise just using the threshold of an energy bin, right?
That's right.
Okay, and so now we have essentially discrete heights of these things of the detection that now give you just a discrete 1 or 0, and all of our electronic noise is gone. And then so I guess the question is, what did the review papers and stuff you're looking at, did they show what that bottom threshold usually is and what it is as a fraction of these other energy heights?
I didn't see a fraction, but I did see a number that I saw 2 or 3 times, 20,000 EV.
Oh, 20 keV. Okay.
Yes.
Is what you would set that bottom to, and you say anything below 20 keV, I don't care if it's a photon or noise, I'm just going to ignore it.
Yeah, typically, yes.
Got it. So that also has the advantage, I guess, it gets rid of some of the scatter, right?
Right.
Okay, cool. All right, great. Thanks. Well, now we all should know about photon counting since we've had 2 good presentations on it. That's great. Let's move on to Chen. Do you want to go next?
Sure. Can you see it?
Yes.
Okay, so I will have to talk about my project about a cardiovascular imaging reconstruction. As I mentioned in the proposal, I was thinking about to do the beam hardening correction for the cardiovascular scan, but it turns out it actually has nothing to do with the beam hardening. It's actually not really a problem in the cardiovascular imaging reconstruction. So I changed my topic and I actually start working on how to make the image looking better. And I will cover this in the slides. So I will cover 5 things. The first is like the flow chart, the whole walkthrough of like how the CT images are constructed. And then I will cover the data correction for the air scan, the cardiovascular scan, and the normalization of fin to parallel conversion, then reconstruction, then the data scaling. So here's a flow chart of the CT image reconstruction. So we started with the sinogram. We got it from the machine. Then also we needed the air scan. Then we correct the data to remove those dents in the data. Then normalize. Normalize basically use your sinogram divided by the air scan, roughly. Then you go to the fin to parallel beam. Then this is reconstruction. So here is the very classic X-ray grid, because for the X-ray, only the detectors want the photons shoot like perpendicularly into the detector. So you need to have those grids to block the photons shooting from other directions to make sure the data is accurate. But the issue is this grid gonna cause some problems on your data. So here's the air scan, like the McVeigh and the Francisco got it from the CT machine. So you can see there's some strips over here. So if you plot like one slice of the sinogram, it looks like this. You can see all those dents. These are the location of your grids. So all we want to do is we need to try to remove all those. I only show you the air scan because, but the cardiovascular sinogram have the similar issue, but it's not as visible as this one. So air scan is like easier to see. So what I do is I need to detect all those dents. So I mark them with the red dots. So I'm just record the indexes of them and try to interpolate and smooth them out. So on the right is like the corrected version for the one slice of the air scan. So I record the indices, and I just use the same index, the same location of those peaks to correct my sinogram too. So these are the exactly same location in the previous air scan dents. So those are the location of my grids. So here is the sinogram. I just mark all of them and interpolate all those points again. So on the right is the corrected version. You can see there's some peaks are removed, but this one is not as obvious as the air scan. But still, this correction is very essential to create a better image. So here's the comparison for the air scan. I'm not showing the sinogram because sinogram is not normalized. So just like a dark chunk, you're not gonna see anything. So here's the zooming version of the air scan of the uncorrected. You can see all those strips because of the grids. And here's the corrected. They're all gone because I removed all those dents. So this should be a uniform air scan. Then we can move forward to the normalization. I think I'm covering the proposal slides. We just basically multiply by the milliamp vector and flip the attenuation, then just divide by the air normalization, not normalization, divided by the air scan, then take the log to flip the intensity. Then when you do the fin to parallel beam, because I think nowadays every CT machine use the fan beam. So you have the beam looks like a triangle, looks like a cone to scan the patient, but this is not gonna work in terms of the data. So we'll have to convert the data from this cone beam into a parallel source to make sure every X-ray enter the detector perpendicularly. So I do this on the MATLAB, and I'm not gonna get into the detail about this because that can be another like 40 minutes talk. So after the fin to parallel, we can finally go to the reconstruction. So here I use the filter backward projection. The left is the dense uncorrected, and the right is the dense corrected. So you can see uncorrected, you can see a lot of rings. That's because of those dents. And on the right, if I remove all of them, then you will get the image on the right. It looks a little bit better, but I'm not saying like that much better. I implemented the algebraic iterative reconstruction too, but I put them two over here. I don't think anybody can tell the difference though. They just look identical to me. So I guess it's like no matter what reconstruction you use, your data actually matters more. Like if you get like really crappy data, no matter how advanced your reconstruction going to be, not going to be helpful. So here on the left one is the iterative reconstructed. The right is the filter the back projection. So compared with the ground truths, I should still have a long way to go. The ground truth looks like really amazing, especially in terms of the contrast, because if you can look at the myocardium and the blood right here, and the fat right here, you can see the huge contrast in the ground truth. It's mine, but mine looks basically like a chunk of uniform material. So then I move to the scaling based on the issue units, like the house field units. So what I did, I threshold them all out. I just separate them all out. I first create a mask, the fat mask. So it has ones everywhere of the fat pixels and a zero everywhere, zero anywhere else. And I use this mask to multiply by my original scan. Then I can extract the fat pixel value out and a zero everywhere. So here, all this gray area are the fat pixels, are fat values. And the black area are just all zero. And did the same thing for the bone. I mean, it's bone, but it's basically calcium right here. So I did for the air and I did it for the blood and the myocardium. So I just basically threshold to segment them out. Then I scale them based on the health field units. So here I multiply the ratio by a negative 100 divided by the average of all those fat pixel values. So negative 100 is around the health field unit for fat, and 1,000 for the bone, and the negative 1,000 for the air. And here's the 40 for the blood and the myocardium. So I scale each tissue separately. Then I just add them up. I just overlay one at the top of another. So fat plus bone plus air plus blood plus like a myocardium. This is kind of like the heart I got. So I did this for the whole scan image. Here's the final result I can get. This is like the best I can get to. It's very noisy. It's like very, very noisy. So you cannot really see the boundary between, or like a borderlines between the fat and the myocardium. But those calciums still visible because I scaled them like way higher. Those calciums are at least like 1,000 values, and the airs that are like negative 1,000. So you can see the huge contrast between them. But here, like those fat, it's really hard to see on my scan. Now I go come to the discussion. The first thing I'm really confused about is the decentering artifacts coming from nowhere. I'm talking about this one, the center one, like right here, the one at the middle. This one, I spent about like a half day yesterday trying to remove it, but I couldn't. I don't know where it comes from. I actually tried to like set the like one row of the sinogram to be 0. If you set a one row to be 0, which means I set the certain pixel location of all slides to be 0, and you will see a like very like bright ring because it's 0 values. And I actually locate the pixel location for this specific ring, but it turns out that value is like very normal. Looks on the slice. It's not like a peak, or it's not like a dense. No, it's just a very normal value. It's pretty close to the adjacent values. That I'm lost. I don't know where this thing comes from. I feel it's from something inside the fan to beam conversion function. I think that's I mean, I was trying so hard to remove, but I couldn't find where it comes from. The second one is the image segmentation. I did this like basically manually. I have no idea how the GE did this. Like GE you input whatever image, they can they can scale the data automatically on its own. They know where the fat is, they know where the tissue is, they know where the bone is. They just can't scale it on its own. So I guess like for this problem, AI and machine learning is probably the way out. Like traditional way is like just so difficult to do, like very hard to implement. And thank you. Here's my reference page and here's my source code. It's public, so everybody can see it.
All right, great. Let's go back to before you did your segmentation of the tissue. Okay, you had an image there. Yeah, forget that. Okay, so here, so this is, let's go, forget algebraic. Let's just look at the version that was reconstructed. Okay, so this is after correction. So this one on the left
Yep.
is as far as we got, right?
Yes.
And you can see sort of that there is the same image underneath it, but it's just that these rings are dominating your signal amplitude, right? So
Yes.
and so the way you would scale these numbers is you don't do it by tissue. You do it once with essentially a water phantom once a day. Remember we said they go in there once a day and they scan water and they set that to 0 and they set air to -1,000, and then everything else falls into place. All of the other pixel values, you don't care what kind of tissue they are. They just take their value that they would when water is 1,000 or is 0 and air is -1,000. But I'm with you on this. It's a mystery why we still have these large, thick ring artifacts or circular artifacts. And I guess one question is, when you did your transformation from your readouts, so your raw data, did you take into account that the detector itself had a certain curvature?
Oh, that might be a good point. No, I didn't.
Okay. So remember that when we did the CT thing and we looked at the different detectors, that it isn't like, if you go back to your picture, you had a cartoon of the fan beam. So go back like 3 slides here, right? So that geometry takes a Feldkamp rebinning algorithm in order to go from the fan beam data to this the data on the right, which is parallel beam data. So that uses, I think it's called a Feldkamp projection or something like that. However, our detector in the GE system has a curve on it, right? So it's not exactly this geometry that we've got here on the left.
Okay.
And so that might be distorting some of the views such that you get this smearing of data all around in a circular direction.
Okay.
But you would think towards the center, it would be less evident, right? And so your image should really get better as we go to the center.
Yes.
Well, so there's probably something else going on as well. And so this was a valiant effort. This is a really hard problem. Why, it gets frustrating trying to work with manufacturers. All of the data you need to do this inversion and reconstruction is in the header of the raw data set. Their water scan, their air scans, all of that stuff, but they won't tell you where it is. So
Yep.
you have to try and figure that out. Okay, but that was a great effort, and you got pretty close. Okay.
Yeah, I just feel like next thing I'm probably gonna work on is just try to use AI. I feel like AI probably is the way out.
Yeah, but you need a ground truth reconstruction to train the AI. It's going to learn whatever transformation the ground truth is doing. And so you still need that ground truth reconstruction, right, to do that. So,
Okay.
or you can just use GE's black box and assume that the image that comes out is good enough.
Yep.
Okay, great. Let's move on then. And thanks for being on time. And who wants to go next? We got, so Jerry, you want to go next?
Yeah, sure. You guys can see the slides all right?
Yes.
Okay. Well, okay, yeah, go ahead and get started. Yeah, my project was to reduce the noise of CT scans using neural network. I'll just keep going. Very brief background. We know that usually iterative reconstruction is used, which uses statistical or other methods to sort of, in a way, estimate or idealize what this data should look like. And this can remove artifacts, such as from metal. Sorry, from this metal implant here. And also previously mentioned that studies have shown that deep learning actually can produce results that are even better than this, with reduced streaking or noise. Right, and it's usually they can be run at a speed similar to iterative reconstruction. And GE first had a commercially approved system in 2019, and I think all the other manufacturers have followed suit. Oh, you know what? Okay. And so my aim here was actually to take these these images that were provided by Professor McVeigh. And this is all from a single, well, basically there was two sets of images. One that was reconstructed using traditional, I think, iterative reconstruction, and then one that involved GE's deep learning plus iterative reconstruction technique. You can see that their technique results in reduced noise while maintaining all the key information. And my plan was to train my own network to sort of learn this transformation here and sort of see maybe which parameters or which key struggles there are in sort of creating this source of neural network noise reductions. And my choice was to use a autoencoder design provided, I think, by TensorFlow. I think I lost the slide. Provided by TensorFlow, and the way that this works is that essentially it'll take the input data and it'll actually compress it into a smaller dimensional space, and then this is called encoding, and then it'll go back again and decode it back into your original sort of image dimension. And using this, well, in theory, it'll learn the key features of your data while discarding sort of unnecessary features. And also, in terms of removing noise, what you can do is you can give it noisy input data and then ask it to decode it or compress it and then decode it into this denoised output data. And that way you can sort of learn the transformation from noisy to unnoisy data. Right, my process, I was using Python, and this example, based on an example from Google TensorFlow, and an autocode example. I first have to convert the images from DICOM to JPEG, and then I use this program called Airfont Viewer, and you can just batch convert sort of all these files. And then this was sort of fed into an autoencoder, and sort of to extract the noise statistics. Like there was a convolutional layer both on the input and the output. And you can see here that it would start from the 512 by 512 image, and then go down to 256 by 256, and then 128 by 128. And it would sort of compress this and then decompress it and learn the sort of process. Right. However, my results were not very good. I think, as you can see, this is the original image and reconstructed. It was very blurry. And I'm not entirely sure why it looks like this. because for reference, this was the sample, like, they would, this is the original and this is after compression decompression, and they would add noise, looks like this. I suspect there's a lot of reasons why this blurriness occurred. Part of it, I think, was that my training data set was still too small. This sample data had about 60,000 images, albeit only at 28 by 28 resolution, like 28 pixels by 28 pixels. So it's very low resolution, but a lot of images. And so I think I only had around 1,000 images between 3 or 4 patient scans, and this maybe wasn't quite enough to learn the encoding and decoding patterns. So
Can I ask
right,
a-
going.
can
Oh
I ask
yeah,
a question?
Yeah.
You go back to the one where you have your image results below the, okay, so these are just different slices we're looking at from right to left, is that correct?
yeah,
Okay. And then, and so this is what came out, and you used, this is your original noisy data. Your ground truth data was the GE deep learning data.
yeah. Or I think what's shown in the slide is just the iterative reconstruction, and then I didn't have time to sort of show the GE data. But I guess this is simulated noise in this case.
Oh, so got it. So the way you were going to do this is you were going to use the GE iterative reconstruction, and you then add noise to it and show you could get rid of that noise. That was the.
No, I think the plan was to use the GE as a base and then use the iterative reconstruction as the noisy version. But I was running into some problems with Google Drive, and like for some reason it was uploading files where like it should have only been 256 images, but for some reason it was reading like 280 or something, and I don't know where it was coming from. It's just technical issues.
I see. Yeah, it looks like you're basically, for your truth data, you've just got the wrong picture or something to get images that look like this, right? They're not close to the actual picture. So either that,
Yeah,
or it's deciding to do a remarkable amount of filtering. Right? It just like blurs it everywhere.
yeah.
Okay.
I think, yeah, I did. Initially, I trained it only on like 5 images that were like consecutive. And it looked pretty good, but then as you add more, you realize it was just learning exactly those 5 images, and it didn't actually extrapolate to new data. So
No, that's
I think I probably just need more samples for it to learn
yeah.
the actual patterns behind this.
So the one thing you can do to make more images, if you need 8 times the number of images, you divide this image, this 512 by 512, into let's say you need 9 times more images, into a 3 by 3 array or something like that, and just run it on those.
Yeah. And I was going to mention, right, definitely I could slice it up into smaller images. And I think this would also help with a different issue, which was that, the sample images were 20 by 28 pixels.
Yep.
So they could get away with training it on the server. But with these much larger images, I suspect, looking at examples online, that you need bigger, basically like a higher latent space in the middle, and like more amounts of parameters.
Yeah.
And I was just running into like all kinds of memory issues, because like I was just trying to increase the number of parameters, but
no, you have to cut out little snippets. You could do like 32 by 32 or something like that and do it that. The other thing is it will learn, it probably doesn't care if you go back to your examples there. It might not even give a damn what the hell's inside the circle as long as it gets the circle right. Because that could be the dominant thing driving whatever's happening, because it's such a high contrast between the black background and that circle. So it's legitimately saying, hey, I'm close, and because it doesn't even look in the middle.
That's also true.
Right. So I think one of the things you'd probably want to do is get rid of the black background and cut out
Right.
little pieces of image that are just image. That's all they are, right?
That's a good point. That's a good point. Yeah.
I don't know. I'm just taking guesses. Okay.
Yeah. Again, I guess just citations. Yeah.
Okay. Is that it?
Yeah, that's it.
Okay, terrific. Thanks, man. And therein lies the, you know, the troublesome days of trying to get a network to learn something, but enough iterations, you finally figure out how to make it work. That's how that goes. Okay. I think we got one more presentation, right? So who has it? You, Sean, are you ready to go?
Yeah, I haven't gone yet.
Okay.
All right. I'll try and make this quick. So my project was on calcification detection with CT while trying to account for motion. We've already, I think, others have already gone over calcification in CT, so I'll just go hit the main points, which is that calcification can be difficult to detect early on, and since CT requires time to take the picture due to the fact that it needs to make a rotation, it can be prone to motion blurs. And typically this is solved via breathing surrogates that may be physically connected to the patient. But I was just wondering, as a project, what may be done mathematically to fix this motion blur. And as a reminder, my original process was to understand the existing methods to simulate coronary motion and try to adapt it. I will say right now that I was not really able to adapt it to more complex data sets, and I'll explain why that is later on. So existing methods, as mentioned before, are primarily made up of two methods, which is either breathing surrogates, which is a physically connected sensor to the patient, that can be used along with the CT sinogram data to reduce or eliminate motion artifacts, or machine learning, which is to feed large amounts of correct data, which is clear images, to try and predict what the final images should be. So most of this will be talking about my own experiment, which is to try and simulate coronary motion. In my case, I set up a image with 4 moving white dots in the corners, and I created 4 of these images where they moved 1 pixel each, and to take 25% of each radon transform and combining them together to make the radon transform of a moving image. So my points of attack to fix this is primarily twofold: to either directly try and fix the image by enhancing contrast or sharpness, or to try and fix the radon transform by using short portions of the data that is in a small enough bracket that you can assume it is correct, to try and predict what the rest of the transform should look like. So I will first talk about what happens if you try and directly process the image. There are 3 ways to try and do this. The first, of course, is to try and see if there's anything that you can fix in the Fourier transform space. The second is to perform direct processing to try and increase contrast, so such that the artifacts can be are less impactful on the on the final image. And the last is to threshold away any of the artifacts, such that that there isn't data in the middle that is unimportant. So here's the inverse radon after including the motion artifact. When you look at the Fourier transform, we actually see that most of the high frequency data has been jumbled, and this makes sense because blurring of any kind is generally just a loss of high frequency data, and in this case we have no real symmetric data to rebuild the blurred parts. So there is no correct way to try and fix this in the Fourier transform. So the only path that I have found, but based on previous experience, is to just delete the portions that are messy. And as you can see, this actually improves contrast quite a bit and removes some of the artifacting. However, this would appear to be the correct way forward, but also we should look at direct processing. So direct processing in this case, the best path forward is to try and enhance local bright spots and filter out the intensities of the artifacting that is unimportant to what we want to detect. And that can be done with a adaptive histogram equalization, which scans the image in a window and determines a local maximas and edges and enhances these edges and maximas. And as you can see, that creates a image that is very similar to the FFT fixed image. And when we compare them, you can see that it's even slightly better at removing some of the artifacts. So finally, the last part of direct processing is thresholding. This keeps only the bright spots of the image and removes extra noise that is unimportant to what we wish to detect. And when we compare the threshold image from the adaptive histogram equalized image and the low pass image, we see that the adaptive histogram image is better at maintaining peak shape and the amount of peaks. And that's what it says here. So next, which is actually the bulk of the mathematical part of this, is the radon transform. We know that the radon transform can be built mathematically. And also when we examine the radon transform of a picture that is in motion, we see that it gains jagged edges where it shouldn't have, and these are essentially what is causing the blurring. And since the radon transform can be calculated mathematically, we're able to take a small slice of the data and to use that to try and recreate the rest of the radon transform. And the assumption is that if we're able to apply this to every highlight, we're able to remove motion blur from critical objects. And this is the projection that I captured versus the projection that I made using a small slice of the original projection. And as you can see, it is very close. However, it actually failed to make the dot in the center. This might be due to needing an even smaller score on the fitting, but it's not a major issue. And when we recreate the image using this new fixed radon, we see that it is in fact much better than the original picture that we captured from the image with the motion artifacts. And if you apply other fixes, we see that all of the points of interest are uniform, and there is no odd separation of peaks. So at this point, I had created my own little phantom to try and integrate some more complicated data with different sized bright spots. And I warped the image outwards to simulate motion. However, this is where things started to go wrong for me, because bright spots in such radon transforms are actually not very clear. And since there are large overlaps of gray areas, they end up appearing brighter on the radon transform than the peaks that we're actually interested in. And this can be seen here. This here is a cross section of the radon transform towards the beginning. And actually, the small peaks on the sides of this transform is actually the points of interest that we're interested in. But because there are much more obvious peaks, these peaks tend to get lost in the noise, or when you try to detect them, it becomes difficult for you to understand data-wise which one is the correct peak. the only reason that I am able to detect to mark out the peaks here is because I know what the data should look like. But theoretically, this should be applied to data that you don't know, and I frankly couldn't come up with a good method to do this detection. And as a result, when you run this algorithm, it ends up detecting the edges between the dark spots and the bright spots in the middle of my phantom, as opposed to just the bright calcified simulated calcifications. And as a result, I found that just even simple thresholding would work better than the algorithm that I ended up creating for this project, and that while my repair algorithm could work, detection is very difficult than I was expecting. And this image on the right here is just applying a simple FFT fix to the original image. And as you can see, even that is a much better contrast than the original image. So my conclusion is that I think radon construction is feasible, but it would need more work to separate the corresponding radon transform portions. And sometimes if a quick and simple detection is what is needed, then simple thresholding and FFT might even work better. My thoughts on the possible future work is that I think machine learning prediction of image reconstruction is a bit problematic, because especially in the case of calcification detection, because you don't really want the AI to start hallucinating calcified spots where there isn't any calcified spot. So I think the correct way forward is to have to develop a machine learning model that detects the correct portions of the radon reconstruction, such that you can make a correct reconstruction without introducing new data points into the image. And that is it. Thank you.
All right, cool. That was a really good attempt at going after motion. If you go back to, let's go back like 3 slides or something like that. I think here. Okay. So, or this one's fine. The interesting thing about motion correction, right? If you're looking for it to get rid of motion blurring from calcium, say in a coronary artery, is that threshold image you've got there. You can use that to determine what set of pixels you should focus on for your motion correction, right? And that gives you a region of the sinogram space that you need to correct. Because let's just say a pixel, right? So if you point to a pixel in the thresholded image and say, you know what, this pixel, I really need to figure out what the motion correction is, and you just try a bunch, right? You know it moved maybe a pixel in whatever direction. So you could just try different directions. You go back to the sinogram, do your fix on the sinogram, and see if it gets better, right? And you iterate that way, such that your ability to find the pixels you need to correct is basically based on your original artifacted image, right? So you could also, in the baseline image itself, without correction, let's go 1 slide back. So here,
This is not the original image.
yeah. So here, yeah, but it's really hard to look at the radon transform, right? This is the problem, is these little dots, once you get into this space, they kind of merge into the background, right? Because they become a sine wave, right? So they're just one cycle of a sine wave. And in fact, they are now a sine wave that, because of the motion, is changing its frequency with time, right? So you get, instead of one full 180-degree cycle or something, you get maybe a bit less or a bit more, but it's impossible to find it in this space. But if you go to if you just reconstruct this thing and then go to your image space, you'll see your artifact image. So go back, say, or one more. Let's just pick up like one that has an art. Yeah, say, here's the artifacted image down in the corner there, or yeah, the one on the left. You know what you have to fix at this point, right?
Mhm.
And so instead of saying, well, do I have to fix every pixel? You say, no, I don't have to fix every pixel. And so most of the motion artifact correction software that is implemented now, you go to the first reconstructed picture that looks like this, and you highlight those dots that are obviously artifacts, right? And that takes you back to the sinogram and where you need to pay attention to the sinogram and how to fix it. When you do fix it, you will generate artifacts in other places, right? Because, the sinogram is sort of a sum of everything, but it does clean up your target, right? So you got super close to doing that. I like the fact you went sinogram space and fixed those sinograms and showed that the artifact got a lot better. So that's great. Nice project.
Thank you.
Okay. That takes us to the end, and so you only have one more thing to do that problem set. Remember, you just have to take a shot at it. And it's kind of a fun little problem anyway. If you want to talk about it, no problem, shoot me an email, we get together. And if it comes around that there's a poll for giving comments on the course, please fill out the comments, like, actually write comments or what you thought about the course. That would be terrific. Otherwise, have a great summer, right? And hope exam week goes well if you have any finals in that week and everything goes well. Okay, it's been really good having you guys in the class. So thanks, and we'll see you later. Just shoot me an email if you need anything. Okay.
Thank you.
Thank you.
Thank you.
Thank
Thank
you.
you.
Guys.